us. So today we're going to talk about, it's honestly our second to last topic that we're ever going to learn. Isn't that crazy? Are you sad? Sean is happy. All right. No, I'm just kidding. So this is called, we're going to talk about electronegativity today. And then on Monday, we're not going to learn anything new. We're really just going to like practice all of the stuff that we've like learned really disjointedly. And then Tuesday and Wednesday, we'll learn our last topic. It's called loose dot diagrams. They're a little overwhelming, so we're going to take 2 days to deal with those. And then Thursday, test review, and then Friday, Unit 11 test, and boom, we're done. So I guess technically we still have school on the 15th for my physical people. Virtual friends, I don't even know if we'll have a Google Meet that day, but they haven't really told us if we like have to or whatever. But you know, for like assignment wise, like we're definitely going to be done by next Friday. So keep that in mind. Another reminder too, if you've missed anything and you want to turn that in, tomorrow being an asynchronous day would be a great day to do anything like that. If you do submit something that's late, just send me a message on Canvas because I don't know to go look for stuff unless you message me. Okay? All right, so let's get to it today, guys. The first document you'll see up here are my notes. You don't necessarily have to download those because I'm going to present those, but if you do want to download them, it's going to take like 2 minutes. It's just a big PowerPoint presentation. The thing that you do want to download is the second document, the notes and practice, and then you also want to download the third thing there that says periodic table with electronegativity values. We're not going to use that until like the end of our notes today, but you do want to have it like available to yourselves. All right, so let's get started. All right, so electronegativity, we're going to talk about the definition first. And honestly, guys, I like to think about electronegativity as basically being the opposite of ionization energy, like sort of, okay? Electronegativity is really the ability of an atom to attract an electron. All right, so if you think about ionization energy really being about like removing an electron, electronegativity is about attracting or gaining electrons, okay? You guys already could technically like think about this, right? If you drew a Bohr diagram for fluorine, you would see that it has 7 valence electrons. You'd probably hypothesize that fluorine has like a high electronegativity because it's 1 electron away from having a full valence shell. All right. We have a scale for electronegativity. It goes from 0 to 4. We'll talk about this a little bit later on. 0 being the weakest, 4 being the strongest. So fluorine, the example I just used, is actually the most electronegative atom on the periodic table, and it has an electronegativity value of 4.0. All right, so pretty easy scale to think about there. All right, let's talk about some kind of connections we can make here with electronegativity. Connections between metals and nonmetals. So metals prefer to lose electrons. They prefer to form cations when they lose electrons. You probably have noticed this. The first 2 columns on your periodic table are alkali metals and alkaline earth metals. And then they form +1 and +2 charges respectively. Okay? Your transition metals, while we don't know the majority of their charges, the charges that we do have written in for like zinc, right? It's a +2. Silver is a +1. So your metals prefer to lose electrons because they become positive ions. Okay? Because of this, they have low electronegativity values. All right? This is just kind of like a connection between the behavior of metals, their valence electrons, and now electronegativity and how it kind of connects back into all that stuff. All right, nonmetals, you've already probably predicted, they're the opposite of metals. They prefer to gain electrons, okay? So we're talking about like oxygen. Oxygen has 6 valence electrons. It has 2 options, give up 6 or gain 2. You know he's gonna gain 2, okay? That's way easier than losing 6. So your nonmetals prefer to gain electrons. When they gain electrons, you know this already, they form ions that have a negative charge, okay? We also know those as anions. All right, strong desire to take in electrons, so that's what correlates to having a high value of electronegativity, okay? fluorine being the highest electronegativity value on our periodic table. All right, let me know if guys if I'm going too fast through the notes today. If I can. All right, so we got two trends. You knew it was coming, right? Didn't you? So your first trend is going down a group, right? So from top to bottom, your electronegativity is going to decrease. All right, so this is the same trend as ionization energy, which can help you kind of remember that. Not that I'm going to ask you to memorize anything, but electronegativity decreases down a group. There's a couple of reasons. The biggest reason is that the atom is getting larger, and as the atom gets larger, you're going to have more electron shielding going on. You're going to have all of those other electrons blocking that nucleus from attracting other electrons. All right, so here's the deal, guys. That nucleus, right, positively charged, it just doesn't really have a desire to gain another electron. It's like, I have enough to deal with here, okay? Think about cesium. Okay, cesium's in the first column, and it has 55 electrons. That is a heck of a lot of electrons. Do you really think cesium wants one more? He really doesn't, okay? He has enough. All right, trend number 2, across a period, electronegativity is going to increase. Again, same trend as the ionization energy, okay? Same kind of reasoning as the other trend, except we're opposite now. So the atom is getting smaller, right? Your atomic radius decreases as you move across. These electrons are held tighter in. And that proton, or the nucleus with the protons, is actually going to want to attract more electrons, okay? Because you have that more concentrated positive charge in the nucleus, okay? For electronegativity, I really like to highlight that fluorine is the most electronegative element. So like as you get closer to fluorine, whether it's moving, from the side or from the bottom or wherever, like as you get closer to fluorine, your electronegativity is going to be higher. All right, so that's just how I like to remember that. All right, so shall we give this a try? We love this, don't we? Yeah, all right, we're getting tired of it. I know we are.
Oh, no, I didn't mean that.
Oh, that's okay. Well. All right, so let's write down though first, electronegativity increases as we go across, and then going down, electronegativity decreases, just so we have that. I like to have that right in front of the faces as kind of a nice little reminder for yourselves. All right, so go ahead and take a minute, take a look at your periodic table. Please do not use the periodic table that I included in your notes today. All right, with the values. We haven't talked about that yet, so don't use that yet. Just use your normal, good old-fashioned periodic table, okay? And I will tell you why I'm asking you to do that in a minute, all right? There's a method to my madness. are you finished? Almost. Take your time. No rush.
I never really know. Some people are really fast with those and others.
All right, let's do it to it. BR or CL, who's got the higher electronegativity? Shout it out.
CL.
CL. Love that. Okay, P versus AS. Shout it out.
P.
Okay, good. K versus CR.
CR.
Yes. Okay, FE versus OS.
FE.
FE, okay, good. And then CO versus SE.
SE.
SE, okay, good. Virtual friends, we got those all right, I hope. All right. Pretty straightforward. You guys have been using those kind of trend comparisons for a few days now. Okay, so here's why we really learn about electronegativity. Not that electronegativity isn't important by itself, but really its connection to types of bonds is really what we want to learn about it for, okay? So we're going to learn about 3 types of bonds. You have some prior knowledge on these bonds, though, because I actually talked about these back in Unit 6, okay? Your ionic bonds basically see a transfer of electrons, okay? You might remember this when we talked about like ionic bonds versus molecular, or ionic compounds versus molecular compounds. All right, we're talking about the same thing here, okay? Ionic bonds form between a metal and a non-metal. And essentially, what we can use now to connect to is electronegativity. So I like to think of ionic bonds as basically consisting of a bully. Because what you end up seeing here is one element has a really high electronegativity, okay? So it like really wants an electron. And then you have an element that like doesn't quite have a very high electronegativity, okay? So that element with the high electronegativity kind of bullies the other element into giving its electron up, okay? So our like common example of this is like NaCl, so sodium chloride. All right, and essentially what happens is sodium has 1 valence electron. Chlorine has 7 valence electrons, okay? What I'm drawing up there for you with the dots is actually what we're going to learn on Tuesday and Wednesday next week, which are the Lewis dot diagrams. I'm not expecting you to know them right now, but just to give you a visual, okay? Chlorine has 7 valence electrons, sodium has 1. You know exactly what chlorine's going to do. He's going to bully sodium and essentially steal or transfer that 1 valence electron from sodium to chlorine. Now, you might be saying, well, why does sodium let this happen? Like, why doesn't sodium stand up for himself? Well, you actually know the reason why. What?
He's outnumbered 1 to 7. He's going to jump.
True. He is outnumbered. The other idea here is also that sodium doesn't actually mind losing 1 electron, right?
Oh.
Sodium has, exactly, right? Sodium has 1 valence electron, so sodium's like, meh, this is okay. I'll allow myself to be bullied. All right.
That's so sad.
It is. It's a little sad.
I'll let it slide.
I'll let it slide this one time. All right, but so this guys is essentially the transfer of electrons. Okay, so just to kind of give you like a little bit of a reference there. All right, now the covalent bonds, they are much nicer. Okay, because the electrons are shared in covalent bonds. Okay. Now, what makes covalent bonds like maybe a little confusing is that you've got polar covalent bonds and you have non-polar covalent bonds. We're going to talk about both of those kinds. But the beauty of this is that you guys will all learn about a polar compound in like the first week of biology next year. Okay. And you're going to think back to this day and you're going to be like, oh yeah, Miss Link taught me all this stuff about polarity. And I wasn't really listening because it was June, but I should have listened. So listen, okay? All right, here's the deal. Covalent bonds are like kindergartners. They're sharing. Sharing is caring, okay? So they're very nice to each other. But the problem is polar covalent bonds show an unequal sharing of electrons, okay? So it's like you've got the two kindergartners and the one's like, here, come play with me. And then he like chucks a ball in the kid's face. Not good, not good, okay? That's what your polar covalent bonds are, all right? So like he's trying, he like invited the kid over, but then he's like,
anger
no,
issues.
yeah, he has anger issues or like he just can't share, okay? So let me show you what happens here. Essentially, we have a bit of a hogging situation going on here, okay? Now, what do I mean by that? One of the elements in the bond is going to be an electron hog, okay? So I'm going to draw a picture here. Feel free to just sit back and watch. You don't necessarily have to draw this. This is a little extra, but I just like to show this to you guys so you have a visual. Here's good old H2O. You will spend at least 2 to 3 days in the first week of biology on H2O. You're going to drive yourselves crazy. You're going to be like, I never knew water had so many things about it. Like, it's so crazy, okay? Here's why it's so crazy. Are you ready for this? Oxygen has a really high electronegativity, okay? And because of that, the electrons spend a little bit more time around oxygen, okay? He's hogging the electrons. Oxygen is the kid who's chucking the ball into the other kid's face. Because of this, oxygen has this partial negative charge, okay? It's not like a full-on negative ion. It has like a tendency to be a little bit more negative than positive, okay? Because of that, the hydrogens that are bonded to the oxygen tend to have a partial positive charge. Cool, right? Like pretty straightforward. Here's what makes this so incredible. When you start having more than one water molecule existing together, because let's face it, we don't ever just really have one molecule of something. What basically happens is an attraction occurs between the partial negatives, so the oxygens, and the partial positives, so the hydrogens. Okay? And so what starts to happen, and you can kind of see this, I'm trying to illustrate it with my dots, is that when you have water molecules together, there's like a lot going on. Okay? There's interactions between the water molecules, and it actually like becomes like a pretty strong attraction between them. Okay? So I don't want to spoil the surprise for your biology teachers next year, but essentially water is amazing and really helps us like sustain life on Earth and not just like in the oceans, but like on land as well. Okay, and it all comes back to water being polar, being a polar covalent molecule. Okay, I have another illustration here for you. It's basically what I just drew. And then this is an interesting picture. This is trying to show you like an electron cloud. All right, and so basically what I'm trying to show you here is that the electrons just spend more time around that oxygen than they do around the hydrogen. All right, nonpolar covalent bonds are probably how like all of you guys were in kindergarten. You're just like perfect, small, tiny little angels who are like, do you want to play with me? And then you like play so nicely with your friends, okay? There is an equal sharing of electrons. This is boring, like nothing exciting is happening here, all right? What?
No fights are arising.
No, yeah, so I'll like to label this as boring. All right, it's really not boring, it's just like nice, okay? The reason behind a nonpolar covalent bond is essentially, let me say this, most nonpolar covalent bonds happen between elements, two atoms of the same element. So like Cl2 is like a prime example, or like H2, like all of your diatomic gases, those are all nonpolar covalent bonds, okay? Here's another picture, here's Cl2, chlorine gas, and basically what you're trying to see here is that there is an equal sharing of electrons. There's no tug of war, there's no fighting, there's no bullying, just nice, peaceful, kind of like hippies or something. Okay, here's the take-home message. We're almost there, guys. I know it's a lot of information. The reason why we care about electronegativity is so that we can figure out what type of bond you have, okay? And this is where that periodic table of values of electronegativities comes in. The type of bond can be determined by examining the difference in electronegativity values. Okay? So we were like talking about electronegativity, and then we're talking about bonds, and here we are putting them together to actually get something out of them. Okay? So what do I mean? Non-polar covalent bonds, when you find the electronegativity values, you're going to use that periodic table I provided for you today, okay? When you find those values, if the difference between the two atoms is between 0 and 0.5, all right, you're going to say, Ms. Link, that is a non-polar covalent bond. Boom, done, question answered. All right, it's a little bit of subtraction. I know math is challenging. All right, but it's really easy math, okay? So for instance, F2, you find fluorine on the electronegativity chart, you would tell me that the value for F is 4.0. So then you do 4.0 minus 4.0 because difference is subtraction. You'd say, oh, their difference is 0. That has to be a non-polar covalent bond. Okay, Sam? If it is 0.5, it's going to be polar, which is the next thing we'll talk about. Yeah. I used inequalities in second block, and everybody was like crying. Is everybody okay with inequalities?
That's hilarious.
It was like, they were like PTSD
Yeah.
people.
Yeah.
Okay. I'm sorry. I'm going to use inequalities again, but I think you'll get over it. All right. So for next, Sam brought up a good question. She said, well, what if the value is 0.5? If the value is 0.5 or anything between 0.5 and 2.1, it is going to be non-polar. All right, so my inequality is here, 0.5 less than or equal to x less than or equal to 2.1. All right, guys, what I'm trying to get across to you is if the value falls right at 0.5 or 2.1, it's going to be polar. Okay. All right. Now, another good question arises here. When you look at H2O, you might be saying, well, Ms. Link, there's 2 hydrogens there. How the heck do I deal with that? You're really only looking at the bond between 1 hydrogen and 1 oxygen. That's what I'm asking you to do here. All right? So oxygen's value is 3.5. Hydrogen's value is 2.1. Whoops. So I do 3.5 minus 2.1, and I get 1.4. Boom. That's smack dab in the middle there. So that is definitely a polar covalent bond. Okay, questions or concerns? It's like pretty straightforward. It's like a nice, like easy process to go through, I think. All right, last but not least, ionic. The difference has to be greater than 2.1. Honestly, guys, I'll tell you right now, you're not going to find too many of these. Okay, a lot of our bonds that we're going to like deal with on like our practice or assignment are going to be polar. Okay, so electronegativity's difference is between, is above 2.1. That really means there's like a big difference between the electronegativity values of the elements. All right, any questions or concerns before we take a look at your assignment? Everybody's okay? All right, so speaking of your assignment, let's check it out. I'm going to do a couple of the questions with you, just because I want to. All right, so here your assignment starts. Sorry that the spacing is so screwed up on this. I apologize for that. Your first 2 questions have to deal with the figuring out the larger electronegativity. You guys know the drill. I like to draw this out. Electronegativity increases as you go across, and then down, electronegativity decreases. All right, you guys should be pretty familiar with figuring those questions out by now. There will be a handful of these questions on your test next Friday, so like it's going to be pretty straightforward, right? As long as you can figure these out now with the tables, then you should be good to go. All right, question 3 starts to deal with the electronegativities, okay? So here's what I want you to do. I want you to find the elements that they list for you. So arsenic and sulfur. Arsenic is 2.0 and sulfur is 2.5. So then you would kind of write in here like, okay, arsenic 2.0, sulfur 2.5. And then you would do that difference, right? 2.5 minus 2.0 gives you 0.5. So I like to write like the difference over here. And then I would circle that has to be polar covalent. Okay, so you're really just practicing doing the differences between the electronegativities and then determining which type of bond it is. Okay, any questions on that? Yes, ma'am.
So do you always minus it by a bigger number?
Yes, that is a really good question. So like it doesn't matter which, yeah, just take the bigger one minus the smaller one. Yeah, good question. All right, question number 4, you're just gonna go back into your notes, guys. It's asking you about your electronegativity trends. Okay, just go back in there, jot some things down. I would like to talk about question 5 together because I find that it's really important and it is gonna be a question on your test next Friday. So it says, why elements of the same group on the periodic table have similar properties? All right, I think I mentioned this on Tuesday, but I'll tell you again. When you have elements in the same group, that means the same column. That means they have the same number of valence electrons. All right, and then that essentially means that they behave the same way. Okay, what you really, 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 really want to know, or what I really want you guys to know, is that depending on the valence electrons of an atom, that like dictates everything. So it dictates whether it's going to form a cation, whether it's going to form an anion, whether it's going to react a lot or not react a lot. Okay, so really just bring it back every single time to number of valence electrons. All right, the last thing that I want to do is just talk about number 6 really quick. Number 6 always confuses people. So they're asking you for the formula for an oxygen to oxygen compound. So that's really just O2, like our diatomic gas. Bless you. And then potassium and bromine is going to be KBr. All right, you're going to go ahead and figure out the type of the bond. All right, and then letter B says, what is different about how these compounds are formed? You want to talk about the electrons. All right, and I'll show you what I mean by that. So if you determine that the bond is non-polar, you're going to tell me that the electrons are equally shared. If you determine that the bond is polar, covalent, you're going to tell me that the electrons are unequally shared. And then if you tell me that the bond is ionic, you're going to tell me that the electrons are transferred. Oops. Okay, so when I say, what is different about how these compounds are formed, really what I'm talking about is how are the electrons behaving? Are they shared? Are they shared unequally? Are they shared equally? Are they transferred? Okay, and you know, you'll figure out the type of bond based on the differences in electronegativity. All right, any questions? Yes, ma'am.
For the O2, would you just minus the O2, like by itself?
Yeah, so you don't know from 0. Yeah. Yeah, we love those ones. Very easy. All right, virtual friends. Actually, everybody first. This is not due until Monday before class. Now, if I were you, I'd just knock it out of the park because it's fresh in your brains. But tomorrow is an async day. I'm not giving you an additional assignment. You can have the day off. My assignment for tomorrow is literally going to say finish your assignment from Thursday. So you can have a nice long weekend, okay? So virtual friends, you are free to go. We will meet on Google Meet all next week, okay? No more Zoom. Sorry, Zoom. We're done with you, Zoom. All right, if you guys need anything, you know how to reach me via Canvas, okay? Have a wonderful weekend, friends, and I will see you on Monday, okay? We buy Felicia to Zoom.
Yep.
Darn right. Darn you, Zoom.
Zoom had it coming, Zoom is all of that for all.